One way the properties of similarity is used is to find the length of an unknown side. So, for example, it can be used to measure things like height of objects that you don't wish to actually measure themselves. So, for example, let's say a tree. Yeah. You want to know what the height of the thing is. Yeah. But you don't want to climb up the tree yourself. So what do? Well, you can utilize the sun. When the sun is in the sky to pass through, it will cast a shadow. So you will end up with the shadow of a tree. Shadow of the tree. Yeah, you can measure the length of that. And at the same time, if you just stick a 1 meter ruler, then at the same time, the sun ray will also cast a shadow. Yeah, let's say the ruler is 1 meter long and the shadow is 1.25 meter long, and the length of the tree's shadow is 5 meters long. Yeah. Well, the idea is that the ratio between the shadows should be exactly the same as the ratio between the height of the ruler and the height of the tree. So we say, well, what's the ratio between the length, the ruler's shadow and the tree's shadow? Well, 1.25 over 5. So you may all be aware it's really, well, we'll have to, no, it should be exactly be the same ratio as 1 over h. Yeah? So the ratio between the shadow of the ruler and the shadow of the tree should be exactly the same as the ratio between the height of the ruler and the height of the tree. In this case, well, we just solve it like normal equation. We want to remove this 5, so we multiply both sides by 5. So 1.25 equals to 5 over h. And then we multiply both sides by h, multiply both sides by h, so we end up 1.25h equals to 5, and finally divide both sides by 1.25, divide by 1.25, and we end up with h equals to 4. Yeah. So just by using the principles of similarity, we could establish the height of the tree. And this is almost exactly the same method Thales used to measure the height of the pyramid over 2,000 years ago. Let's try something much more, well, how should I say it? Much more synthetic. It's completely unnatural, and it's entirely the product of abstract thinking. Let's have a triangle. Yeah, so it's a right angle triangle. One side 1.875, other side 1.5, cross, dot. And let's have another larger triangle. Also right angle, with 20 here, x here, and 12 here, dot, cross. Well, in this case, well, we've been told that these two triangles are similar because all matching angles are the same, so they have to have the same shape. Well, look, the tricky bit, okay, so this side is also unknown. The tricky bit here is now identifying matching side. So let's look at 1.5 here. 1.5 is between the cross and the right angle. So correspondingly, the same one here is 12, because it's also between the cross and the right angle. So we write it as 12 over 1.5. And that's the scaling factor, which is 8. That's the scaling factor of the triangle. So this is 8 times this. Now, if these are similar, then the ratio between other two matching sides have to be the same as well. So let's look. 20 over y. So let's say 20 over y. The hypotenuse over the hypotenuse also have to be 8. Yep. Once again, solve it like in a normal equation, times y, 20 equals to 8y, divided by 8, divided by 8, and y equals to 20 divided by 8 is 2.5. And similarly for the other unknown side, x over 1.875. X over 1.875 also has to equal to 8. And this way it's quite straightforward. Times 1.875 times 1.875. And we end up with x equals to 8 times 1.875, 15. So just by using the principles of similarity, we could establish the unknown sides on various figures.